Welcome to week 4, chapter 5, sampling distributions. Chapter 5 is about sampling distributions, and we will go one by one through all these points. First, we will understand about word statistical inference. So from the last few weeks, we are studying about parameters and statistics, and now I think you know what is the difference between parameters and statistics. So here is just for your review that parameter is a number that describes some characteristics of the population, and in statistical practice the value of parameter is not known because we cannot examine the entire population, whereas a statistics is a number that describes some characteristic of a sample. The value of statistic can be computed directly from the sample data, but it can change from sample to sample. We often use a statistic to estimate an unknown parameter. And to remember these things, it is saying that because sample starts from S and statistics start from S, so it's just giving you some inference that statistics come from samples and parameters come from populations. And we write mu, that is the Greek letter mu, for the population mean and sigma for the population standard deviation, whereas x bar for the sample mean and s for the sample standard deviation. So here is an example from the book. It's telling you about the understanding the college student market. Since 1987, Student Monitor has published an annual market research study that provides clients with information about the college student market. The firm uses a random sample of 1,200 students located throughout the United States. One phase of the research focuses on computing and technology, and the firm reports that undergraduates spent an average of 19 hours per week on the internet and 88% own a cell phone. The sample mean of this sample is 19 hours, and this is a statistic. The corresponding parameter is the average, called it mu, of all undergraduate enrolled in 4-year college and universities all over United States. And similarly, the proportion of the sample who own a cell phone, because we got the inference from here 88%. So here it is a proportion of sample. For the proportion of sample, we use p hat. And here it is telling you about 1056 students in the sample, in 1200 number of students of sample. Therefore, we got 88%, and this is a statistic. And this is a new statistics for you. So proportion of the sample is p hat. Whereas for the corresponding parameter is the proportion called it P of all undergraduate at 4-year college and universities who own a cell phone. We don't know the value of the parameter mu and P, so we use the statistics x bar and p hat respectively to estimate them. So statistical estimation, the process of statistical inference involves using information from a sample to draw conclusions about a wider population. Different random samples yield different statistics. So if we have a population like in the earlier example, there are so many different students in United States and we got 1200 students. So if we are going to get a sample, each time we can get a different sample and the different statistics will be there. So we need to be able to describe the sampling distribution of the possible value of a statistic in order to perform statistical inference. So the sampling distribution of a statistic consists of all possible values of the statistic and the relative frequency with which each value occurs. We may plot this distribution using a histogram, just as we plotted a histogram to display the distribution of data in chapter 1. So if here is a population, we are getting the sample. We will collect the data from representative sample and we can make an inference about the population. So sampling variability is a term that is used for the fact that the value of a statistic varies in repeated random sampling. So what does this mean? It means that from a population, if you are getting a sample, so if for the statistic we are taking mean, so the mean of this sample may or may not be equal to this sample or this sample or this sample. So that is a sampling variability. We will understand this by an example later. Now the sampling distribution. So if we measure enough subjects, the statistic will be very close to the unknown parameter that it is estimating. If we took every one of the possible sample of a certain size, calculated the sample mean for each and made a histogram of all of those values, we would have a sampling distribution. The sampling distribution of a statistic is the distribution of the values taken by the statistic in all possible samples of the same size of the same population. So in practice, it is difficult to take all possible samples of size n to obtain the actual sampling distribution of a statistic. Instead, we can use simulation to imitate the process by taking many samples. And this is also a very expensive thing to do because we cannot sample if in earlier example, if we have to take like all the students of the United States, so it would be very expensive to take different samples again and again. So now here is an example I created from Excel, and I created almost 1,000 values with the random rand between function and taking values from 40 to 120, and we can assume that these 1,000 values are our population and these are the weights. And for that, from there I got 5 samples and they all are of same size, that is 50. And after that, when I calculated their mean, what you can see that their mean are not equal, and they are not equal. What this shows, this is the sampling variability. And if like this I take like 10, 20 or 30 samples from this, we then after that from this statistic, when we plot a histogram, it will be known as sampling distribution. So bias and variability, we can think of the true value of the population parameter as the bull's eye on a target and of the sample statistics as an arrow fired at the target. Bias and variability describe what happens when we take many shots at the target. So here we can see in this figure, there are four different figures. So first we will understand what is bias and what is variability. So bias is the concern, the center of the sampling distribution. A statistics used to estimate a parameter is unbiased if the mean of its sampling distribution is equal to the true value of the parameter being estimated. We will learn about the unbiased estimator later. And the variability of a statistic is described by the spread of the sampling distribution. This spread is determined by the sampling design and the sample size n. Statistics from larger probability samples have smaller spreads. And here we can see that the ideal case is this option D, in which there is no bias and variability is very low, and we got our population parameter from the sample statistics. But when we see other, here this is an example of high bias and low variability, whereas low bias and high variability is showing from the spread of these values, whereas you can see here high bias and high variability with example here. Now the question arises, can we manage this bias and variability? So a good sampling scheme must have both small bias and small variability. So to reduce bias, we use random sampling, and to reduce variability of a statistic from an SRS, that is simple random sample, we use a larger sample. The variability of a statistic from a random sample does not depend on the size of the population, as long as the population is at least 20 times larger than the sample. So why we randomize? The purpose of sample is to give us information about a larger population. So the process of drawing a conclusion about a population on the basis of a sample data is called inference. Why should we rely on random sampling? First, to eliminate bias in selecting sample from the list of available individuals. Second, the law of probability allows trustworthy inference about the population. Results from random sample come with the margin of error that sets bound on the size of the likely error. Larger random samples give better information about the population than the smaller samples. Now, the sampling distribution of a sample mean. So population distribution. The population distribution of a variable is the distribution of values of the variable among all individuals in the population. The population distribution is also the probability distribution of the variable when we choose one individual at random from the population. So in many examples, there is a well-defined population of interest from which SRSs can be drawn as when we sample students who attend a particular university. So, however, sometimes a population of interest does not actually exist. For example, exam scores of students who took a course last semester can be thought of as a sample from a hypothetical population of students who will take the course in the future. But that population of students does not yet exist. So we can still think of the observation as having come from the population with a probability distribution. Now, mean and standard deviation of sample mean. So mean of a sampling distribution of a sample mean, there is no tendency for a sample mean to fall systematically above or below mu. Even if the distribution of raw data is skewed, thus the mean of the sampling distribution is unbiased estimate of the population mean mu. And standard deviation of the sampling distribution of a sample mean. The standard deviation of the sampling distribution measures how much the sample statistic varies from sample to sample. It is smaller than the standard deviation of the population by a factor root n. So averages are less variable than individual observation. So I just want to explain why, because we are saying here particularly the mean of the sampling distribution is an unbiased estimate of the population mean mu. So why it's an unbiased estimate? We will understand this. So we are studying from different weeks that there's a population, there's a parameter, and if this is our population, so and this smaller one is our sample, then we use population parameter that is equal to mu, whereas for the sample we use x bar. For x bar we know our formula is 1 by n summation sign I is equal to 1 n xi. It is the same thing that we call average and add every values and divide it by the total number of observations. So this is the same thing. And now we also call population parameter as expected value of xi. So it is represented as E xi. Now when we want to get the mean of our sampling distribution, so how we can write it? We can write it E x bar, and we know the value of x bar is 1 by n, and the summation and all these values xi, and then we can write 1 by n summation E will be inside with xi. Now this exi is the similar to mu, so it will be the 1 by mu, and because of the summation it will be n mu. Both n will be cancelled, and here we can see that Ex bar is equal to mu. So that's why we call it unbiased estimator. So the sampling distribution of a sample mean, when we choose many simple random samples from a population, the sampling distribution of sample mean is centered at the population mean mu and is less spread out than the population distribution. And the facts are, the sampling distribution of sample means, suppose that x bar is the mean of an SRS of size n drawn from a large population with mean mu and standard deviation sigma, then the mean of the sampling distribution x bar is mu x, that is equal to mu. And the standard deviation of the sampling distribution of x bar is sigma x is equal to sigma by root n. We should remember these value formulas. And if individual observation have the distribution, that is a normal distribution with mean mu and standard deviation sigma, then the sample mean of n simple random sample of size n has the normal distribution, that is with mean mu, but standard deviation will be changed to sigma by root n, and it doesn't matter what is the size of the sample. So here is the example, and here we can see if here is a population with mean mu, and we are getting our samples with different x bars, and here's a sampling distribution. This is the mu, that is equal to mu, and this is standard deviation, but its formula is sigma by root n. So the facts about sampling distribution of x bar: its sampling must be simple random samples, and mean exactly equals mu regardless of population shape or sample size. Standard deviation of x bar is always less than the standard deviation of the population for samples of any size where n is greater than 1. Why? Because we have seen that because the population standard deviation is sigma, whereas the sampling distribution standard deviation is sigma by root n. And standard deviation of x bar gets smaller as n increases at rate root n. To cut standard deviation in half, quadruple sample size. So what does this mean? Because if we are quadruple size, because for root 4 we will got the values 2. So it is saying standard deviation in half. To cut it, we have to quadruple sample size. Shape is normal if population is normal for any sample size. So if we want to know if the population's shape is normal, then sample size shape is always normal. So we don't need to understand about the sample size, what would be the shape of the sample size. Shape is approximately normal if we take a large random sample from a non-normal population. This point is very important because from this point we will learn about the central limit theorem. So here is to sum up, we can see again the center. What would be the center? The mean of the sampling distribution of x bar equals the population mean mu. Spread, the standard deviation of the sampling distribution of x bar equals to standard deviation by root n. Whereas shape, when the population is normal, the shape of the sampling distribution of x bar is normal. But when the population is non-normal, the shape of the sampling distribution of x bar is approximately normal when n is large enough. So this is the, as I explained earlier, this is the theorem we are going to explain. So here is the central limit theorem, and for the shape we have to understand this thing, that if you are taking a large simple random sample of size n from any population, then the sampling distribution of x bar is approximately normal. But shape gets more normal as n increases. What's the value for that? N is greater than 0 is considered as large enough. And central limit theorem, which is also known as CLT, allows us to use the normal curve to compute approximate probabilities of x bar. So if our population is skewed, here we can see here, but if our sample is large enough, then it will be normal. So here is the example. We can see our population is right skewed, and here we can see that its mean mu is equal to 26, whereas sigma is equal to 20. For the sampling distribution, we can see when n is equal to 4, it's still skewed. And what will be the mean? Mean is still 26, whereas the spread would be 10, because sigma by root n, 20 by root 4 is equal to 10. And what is the shape? It's still right skewed. Now here, when n is equal to 16, now we can see specifically that it's getting to normal. And this is mu is equal to 26. now standard deviation is 5 and it is slightly right skewed. But as n is equal to 32, and here we can see we are applying central limit theorem, and here we can see that this is now almost normal, and mean is equal to 26, whereas the standard deviation is 3.5 because 20 by root 32 is equal to 3.5. And for larger sample size, we can see n is equal to 64, and it is way almost normal, and its standard deviation is very small. So mean is 26, but standard deviation is sigma by root n, that is the 2.5, and this is almost normal. So to summarize, we can say means are equal for all n, whereas standard deviation of x bar decreases as n increases because we are dividing it by root n, and shape of sampling distribution of x bar becomes more normal as n increases. So when we saw earlier in the examples that when our n was equal to 32 and we can apply their central limit theorem, and our shape is almost normal, and as the size is increasing, it's getting to more normal. So now, do we have to create the sampling distribution of x bar every time we want to compute probabilities on x bar? So no, we can apply the central limit theorem and use the normal curve to find probabilities. But now the formula would be changed. We know z is equal to x for the normal distribution. We have applied this many times. So z is equal to x minus mu divided by sigma. That is the basic formula. That is variable value minus mean divided by standard deviation. But here for the sampling distribution x bar, z is equal to x bar, that is the value, minus mean of x bar and divided by the standard deviation of x bar. And now formula is x bar minus mu divided by sigma by root n. So here's an example, and we try to understand what it's saying. So it's a creamery. It sells bottles of chocolate milk with mean weight 1.0875 pound and standard deviation of 0.015 pounds. The weight of these bottles are normally distributed. What is the probability that a randomly selected bottle weighs more than 1.1 pounds? So which formula we need to put here? We will put the formula we were using earlier. So we will use x minus mu divided by sigma, and we already have done these things earlier, so you can understand it. Here we can write 1.1 because we want to know the value of more than 1.1 pounds, minus mean 1.0875 divided by 0.015, which gives us the value 0.83. And for the z-score table, when we see the value of 0.83, we will get here 0.88, 0.83, 0.7967. And because we have to get more than 1.1, so we have to subtract it with 1. So we will get 0.2033. So in this example, we can see it's saying that the same thing, weights of bottles of chocolate milk are normally distributed with mean mu and sigma 0.015. What is the probability that mean of a random sample of 8 bottles of chocolate milk exceeds 1.1 pounds? So what is the distribution of x bar? That would be normal, because it's already telling us that it is normally distributed. It's telling you that it is normally distributed, and population is normal, and sampling distribution of x bar is normal with mean mu, that is 1.0875, whereas sigma would be sigma by root n, that is 0.015 by root 8, and the value would be 0.0053. So when we put all these values here, we will get the value 2.36, and we will get the same, do the similar things we did earlier. And now we are getting the value of 2.36, that is 0.9909. We will subtract it 1 minus 0.9909, and we are going to get 0.0091. So here we can understand how we used the different formula here. Now here is one other example. Earlier in the example there were 8 bottles. Now we are seeing that it is saying earlier in the example it was saying that our population was normally distributed, but here it is saying that the right skewed distribution is there with mean mu 26 whereas sigma is equal to 20. What is the probability of the mean price of a random sample of n is equal to 32? Here now we can apply central limit theorem, and by central limit theorem we know now we can use the earlier formula, because we are using central limit theorem and our distribution is approximately normal. So here what we will do, mu is equal to 26 whereas the standard deviation 20 divided by root 32, it's equal to 3.54, and then we can draw and label normal curve, and we can compute our z-score, that is minus 3.11, and we will see the value of it, and it is 0.0009. So we have to keep in mind, if it is more than 30 we can apply central limit theorem, though population is not normal, but still we can apply the same formula because of central limit theorem. So now it's telling us predicting sampling distribution of x bar. So in statistical practice, we can take only one sample of size n and use sample results to make inference about the population. Why don't we need to create sampling distribution of x bar? Because we know mean is equal to mu and standard deviation is sigma by root n. So shape is approximately normal if sample is large enough, and SRS by central limit theorem. These facts allow us to specify the sampling distribution of x bar without creating it. And we don't need to know the shape of the population because of the central limit theorem. We are saying if our sample is large enough, that is greater than 30, then we can apply central limit theorem and can do inference on mu based on x bar from one sample. So here is a visual. We can see again that our population is right skewed, and sample, if we are taking one sample, that is x bar, we are getting value 27.07, s is equal to 18.47, and when we are taking more than 30 samples, where here we can see n is equal to 32, then mean is equal to 26, that is equal to the population, where sigma by root n, that is 20 by root 32, that is 3.53, because always sampling distribution standard deviation will be less than the population standard deviation. Now we have to remember these things. What's the center of the population? It's mu. Center of the sample, x bar. Center of the sampling distribution of x bar equal to mu. When we are talking about spread of population is sigma, spread of sample is s, spread of sampling distribution of x bar is sigma by root n. About the shape, population shape can be non-normal or normal. For the sample, get closer to population shape as n increases. For sampling distribution, approximately normal if n is large enough, or normal if population is normal. So probability using normal curve, only population is normal. Here we can only use if population is normal. And for the sample we cannot use, but only if sampling distribution is approximately or exactly normal, we can use probability using normal curve. Now here's one more example of central limit theorem, and here it's saying that based on service records from the past year, the time in hours that a technician requires to complete a preventive maintenance on air conditioner follows a distribution that is strongly right skewed and whose most likely outcome are close to 0. The mean time is mu is equal to 1 hour and standard deviation is sigma is equal to 1. So your company will service an SRS of 70 air conditioner, and you have budgeted 1.1 hours per unit. Will this be enough? So what we will do? We can understand this particularly. What we can apply because of the central limit theorem. Though population is skewed, we will take our formula that we used for the normal distribution, and here we can apply it here. So for the mu, we know mu is equal to 1, whereas for the mu, for sigma for x bar, it is sigma by root n, that is 1 by root 70, that is equal to 0.12. So if we are going writing it as normal distribution with mean 1, whereas standard deviation 0.12, so we are going to get the value. Here we can see, if we are going to put all the values here, we are going to get it 0.83, and when we see it in the our z-score value, we will get probability of 0.2033. So if your budget is 1.1 hour per unit, there is a 20% chance that technician will not complete the work within the budgeted time.